Okay, thanks, Cece. All right, so since I forgot to record this, I'll remember to save this whiteboard at the end, and I can just post the whiteboard online. Okay. Cool. So let me switch gears, and remember we've been talking about separation of variables. Okay. And in the recorded lecture that I posted on Wednesday, I talked about, in particular, eigenvalue problems, okay, that emerge from separation of variables, okay? So I'm just going to sort of base this on a book problem here, okay, where we have Robin boundary conditions. So what are the three main types of boundary conditions that we've talked about so far, right? So let's say we're doing the heat equation, okay, with boundary conditions, okay? And let's say the heat equation lives on 0 to L, T greater than 0, okay? And then our BCs, right, could be U of 0, T equals U of L, T equals 0. This would be called Dirichlet boundary conditions. They could be Neumann. So U sub x 0t is equal to, I'll put a minus sign, but it doesn't really matter because I want that to be a flux. Neumann boundary conditions just means that the spatial derivative goes to 0. So that essentially just means physically, as opposed to Dirichlet. Dirichlet would be like you have physically some absorption of the heat, right? So you have a bar here, right? And maybe you have something cooling the ends of the bar to 0 degrees and whatever your units are in, right? Maybe they're interfacing with an ice bath here or something like that. Okay, Neumann boundary conditions. Sometimes these are called insulating boundary conditions, and it just means that the heat is trapped, okay, within here, so it cannot leak out. So the heat will diffuse and it'll spread out, but you won't lose any heat as you would from absorbing boundary conditions, okay? The boundary conditions then that are kind of in between would be what are called Robin boundary conditions, okay? Ux of 0t minus a0 u 0t is equal to 0, and u sub x l t plus al ult is equal to 0, okay? This is for t greater than 0. These are what are called Robin boundary conditions, okay? Or you might say partially absorbing, okay? Which just means that maybe you have some insulating material at the end of your bar or whatever the medium is, but it does not perfectly insulate the material. So you get some leakage of the heat out the side, okay? So, fine, so this is a Robin boundary condition. And as you might imagine, you get kind of this nice clean eigenvalue problem in the case of absorbing boundary conditions. We've seen that before, okay? We haven't really talked about the Neumann boundary condition. I might give you a practice problem on the next homework on this, okay? We're gonna look in a practice problem now just on how to handle the Robin boundary conditions, okay? And so the idea then, I can find it here, okay, is that if we apply separation of variables, for Robin boundary conditions, I know I'm doing like a super long setup to this problem, but some opportunity to review material, okay? Then we can say U is going to be equal to W of T V of X, okay? So if I plug that in, then I get W prime of T V of X is equal to K W of T V prime prime of X, okay? I can rearrange this as before, right? So I get W prime over K W is equal to V prime prime over V is equal to some constant I'll call minus lambda, okay? So because this is just a function of T, this is just a function of X, these have to be constant in order to equal each other. So we just say that they're equal to a constant, and we'll make it that constant negative lambda, okay? So if I just take out the X equation, then what I get is V prime prime plus lambda V is equal to 0. And this is true on 0 to L, okay? And that's what we're going to talk about for now. Now, if I apply Robin BCs, okay, how is that all going to fit together? Well, I just get W V prime at 0 minus A0 W V of 0 is equal to 0. I can divide out by the W, assuming that it's not 0, and I just get V prime of 0 minus A0 V of 0 is equal to 0. And I would get a similar equation for L, right? So I'm going to write it up here. So at X equals L, I'm going to have V prime of L plus AL V of L is equal to 0, okay? So don't worry, I'll write it all on the next page, okay? So now, right, this is the eigenvalue problem I have. So now we're just really going to focus on a differential equation, second order, right? And it's an eigenvalue problem because I don't know what lambda is. I need to pick my lambda so that it works. Okay. So this is my eigenvalue problem. And now you're sort of in the realm of how to deal with this problem. So after this long setup, right, of our eigenvalue problem, okay? Let's start by essentially trying to, I kind of want to give this to you in piecemeal, so I don't necessarily want to give you all of this at once, okay? I want you to derive a formula for K, where minus K squared is equal to lambda, okay? And this should be using the above eigenvalue problem, okay? Why don't we work on that maybe for 10 minutes? All you're gonna do is just plug in this assumption, okay, into the above equation, right? I'm gonna solve for the homogeneous solutions to this